All right, this is to go over the test for Chapter 6-7 for 2020, our favorite year. All right, so the first question in my test, remember your test could be different. Please number your test corrections by your numbers, not my numbers. The same force pushes in 3 different ways on a box, moving at a constant velocity as the drawings show. Rank the work done by the force F in ascending order. So the smallest one is C because it's perpendicular, right? So C is perpendicular to V, so therefore that means that the work is equal to 0. And then the next one would be A, right? Because with A, and this was the force, right? With A, the force is at an angle to the way it's moving. And so the work would be equal to F x cosine theta. And since there's a theta and cosine is less than 1, that would be less work. And then for the last one, B has the most work because F is parallel to the way it's moving, and so your work would simply be equal to F times X. So that's the biggest, then that's the next biggest, and that's the smallest. A non-zero net force acts on a particle and does work. Okay, so the important part here is it does work. So if it does work, then the force has to be in the direction it's moving. So if here's my object, if it's doing work, if we know that the force is doing work on it, it can't be perpendicular. And therefore, it must be increasing its kinetic energy because it's moving in that direction. So it has to increase, it has to change its kinetic energy. I guess it could make it go down too. It doesn't really say, it just says it's non-zero net force. So therefore, the kinetic energy has to change. I guess you can't really say if it goes up or down, but the kinetic energy has to change. But kinetic energy is equal to 1/2 mv squared, and you know this isn't changing, so that means you must have a change in your speed. Because remember, kinetic energy is speed, not velocity. And well, if it's speed, then we know that means you have to have a change in the velocity because velocity is speed plus direction. So you can change velocity without changing speed, but you can't change speed without changing velocity. You can't change kinetic energy without changing speed. So that's kind of where the logic comes from. And then for this one, this is a person that's jumping. He clears the bar and he's going to land on an air mattress, which is much better than the concrete. So you had to use the concepts of impulse momentum. So the idea is that the impulse in both cases is m delta v is the same because his mass is the same, or her mass, sorry, and her change in speed goes from wherever it was to 0. So that's the same. But we also know that impulse is equal to F times t, and it tells you that the stopping time would have been much shorter. So by increasing the time with the mattress, we decrease the force. So that's what you need to say. Now for number 4, there's 2 ways to do it. The easiest way to do this problem, which I keep trying to push you guys to do, is you just say work is equal to the change in energy. In this case, it's going up, so it's just equal to mgh. And then I can look at this and I can go, okay, here's my little triangle. That's h, that's s, that's theta. So I can see that h over s is equal to the sine of theta. And so therefore I can solve for S, right? However you want to do it, right? So I can plug in my work because I'm given work, I'm given mass, I know acceleration of gravity, I can find H and I can plug it in there. But a lot of you like to do it the other way, the hard way. And so you say, okay, here is my object, and I know that there are 2 components of gravity, and so I know that there is, well, gravity is pointing straight down, and so I can do this, and this is Fg, and this is my normal force up here, And I really should have these in different colors because those are components, right? And so I know these two components don't do any work. They're perpendicular, so I don't care about them. So I can say, okay, that one's FG sine theta. And then I know that's how hard I have to push. So therefore my work is equal to FG sine theta times S. I would not do it that way, but if you really want to, you could do it that way. Do not, this is an example where you can't just say work equals fx cosine theta, because see, it's sine theta in this case. So anyways, I think this is the easier way. And this one says that we have this bicyclist and they're traveling at a speed of 20 meters per second. And now they're going to coast up the hill. So we're using conservation of energy. So here's my hill. Here's my bicycle person. All right, terrible bicycle person. Yay. And he's going to, or she or it is going to get, I think it becomes a him, gets to the top. So we know that they have kinetic energy here and potential energy. So all we have to do is say, oh, it's 1/2 mv squared at the bottom, mgh at the top. And so I just say, oh, 1/2 mv squared equals mgh. I can then cross off my m's and I can solve for h, right? So h is equal to, do it carefully, v squared over 2g, right? So that's the easiest way to do that one. It does give you the mass later, so you could have put the mass in, but you can see the mass doesn't matter. So so this is A. And then for part B, you're trying to find the power. So power is change in energy per time. It says he stops. We know the time. The energy is going to be potential energy. So it's just going to be mgh over t, just like your horsepower lab. And then the explanation, what's the same, what's the difference? In both cases, the bicyclist is gaining potential energy, but in A, they are changing kinetic energy into potential energy, whereas in B, it's the person applying work, doing work with the pedals, that causes the increase in potential energy. So you can't get energy from nowhere. In one case, it comes from kinetic energy, and in case B, it comes from the work of the bicyclist. He ate his food, hopefully, to get energy to his muscles. Center of mass one, this one shouldn't have been too bad. You just had to do the sum of the xm's on the top. So in this case, so it's the sum of the xm's divided by the sum of the m's. So in this case, it was 4.5. Oh, I'm never going to fit this one. 4.5 times 9 plus 2.3 times 6 plus 4.5 times 1, and you just divide that by the total mass. So 4.5 plus 2.3 plus 4.5. So this is all on the top of the fraction. That's on the bottom of the fraction. You divide, you do it right, it comes out to be 5.2 meters. And then you had to explain what happens to the center of mass. So if I move this one in that direction, right, it's going to make the center of mass move in that direction. So it's going to be harder to balance, right? It's going to move up that way. And then, but if you move the center of mass, as far as a linear impulse, it doesn't matter. It's still got the same mass, just like our block that went flipping around. It might turn differently, but the linear momentum would be the same. So that's the whole point of center of mass, is while you move it up and down, wherever it happens to be, the direction the center of mass goes, and if you're looking at the change in momentum, is going to be the same. This last one was graphing, because you know I'm always going to do something with graphs. So this was a forced time graph. So the easiest way to do this first question, which is so again, remember, you have to remember it has momentum to begin with, right? So it has momentum initial over here, and then after the impulse, right, you put a force, so I'm going to push it on, I'll have a jetpack on it, I don't know. Anyways, you're going to have a momentum after. That's the concept. is it was moving, it had momentum. I pushed on it with different forces, right? So it was at a high force, and then it was at a low force, right? For different amounts of times, so I can see what the times are. And so that's going to give me a final momentum. But what I'm looking for is the impulse. And so you could do, the easiest way to do it, like I said, is impulse is equal to the area. So if you look at it, it's simply 6 times 6, because that's that first square, right? If I look at this part, this is a 6 by 6 square. And then the second part down here is I know it's hard to read on my tiny little screen, is a 3 times 2 force, or 3 times 2 block. So 3 times 2, which comes out to be 36 plus 12. No, 36 plus 6, which equals 42, right? Newton seconds. You also could have just said, well, J is equal to Ft, but the thing is, there's 2 Ft's, they're not the same force, so, but you'd get the same answer. You'd have Ft for the first force plus Ft for the second force, but it still comes out 6 times 6 plus 3 times 2, so it's the same answer, all right? And your explanation should just be something about the area. The area under the curve represents the impulse, because that's force times time, or force times time is impulse. And then this is the one that is harder, because you have to remember it had momentum to begin with. I added some impulse, and that led to my final momentum. So you can't just say, oh, what a lot of people do with this one is they say, okay, my momentum is equal to, or my change in momentum is equal to 42, and then I'm going to set that equal to m times v, because it gave me m, because the problem is it's m delta v, so it should be J is equal to m times Vf minus V naught, and so we're trying to find Vf, so Vf is equal to J over m plus V naught. So you have to add the initial velocity, which I believe was 5 meters per second, to get the right answer. All right, that's it.